Relax. So we start the lesson. Okay. Okay. So yesterday we discussed about up to electric field strength, right? Okay. So first we talk about electric force, Coulomb's law. It looks like same as Newton's law of gravity. Just the difference is charge. So Coulomb's law said what? The force between 2 point charges. You must say point charges. The force is directly proportional to the product of charge and inversely proportional to the square of the distance. Okay. And we talk about electric field strength, the same old definition, the same definition. What is electric field strength? Is defined as the force per unit positive test charge. Okay. Both quantities are vector quantities. And we derive for non-uniform field two formulas. Okay. For the force is KQQ over R squared. And for electric field strength is found to be KQ over R squared. Okay, KQ over R squared. The Q is the center charge. Okay, center charge. Okay, today's lesson is going to be a little tricky. We're going to talk about electric potential. Okay, electric potential energy. Okay, what is electric potential energy? So recall back, I already told you earlier, electric potential energy same as gravitational potential energy. What is electric potential energy? Is energy. It's energy U. We put a symbol U. Is for a positive spherical charge. Is for positive Q at a particular point is defined as the work done on the charge in moving from infinity to that point. This is not electric potential. This is electric potential energy. Okay, electric potential energy. So electric potential energy is the work done from infinity to R. It is the derivation law. Integration of FdR. FdR is force times, work F times distance travel. Integration is the area under graph law, right? Force versus distance travel, the area under graph, we do integration, right? The integration is the, what do you call, potential energy, potential energy. So through integration, so negative Fs, so negative KQQR, finally you will get this formula, this formula. The derivation is not important. The important is how do you use this final formula, okay? The final formula, as I said, recall back for gravity. For the gravity, what is gravitation potential energy is negative GMM over R, negative GMM over R. So same as electric potential now is K QQ over R, okay, same format. But electric potential energy will have gravitational potential energy will have negative. It's always negative. Electric potential energy, no negative. Okay, electric potential energy. But mass is replaced with the charge. Okay, so for a positive charge, a positive test charge, the electric potential energy here is positive or negative. It's going to be a positive value or a negative value. When we use electric potential energy, remember the nature of the charge, the sign of charge need to be included. Okay, what need to be included? The sign need to be included. Okay, last time I told you for force, no need to include the charge sign. K Q1 Q2 over R squared. No need to include the sign of charge. For electric field strength also, the KQ over R squared. The Q no need to include the sign of charge. But for electric potential energy, the sign of charge need to be included. That means if this is positive and the test charge is negative, then test charge you have to put as negative. Your final electric potential energy is going to be negative. Okay? So KQQR. Please include a sign of charge for electric potential energy. Very important. Okay. So if this is a positive charge, it's a positive charge. Okay. Let's say electric potential here is positive 10 joule. Okay, positive 10 joule. Can you suggest a value for electric potential here when the charge is being here? Going to more than positive 10 or less than positive 10? The work done to drag the test charge from there to here is the potential here. So how much more than 10 or less than 10? Anyone? What is electric potential? The work done to bring a positive charge from infinity to that point. Okay. If the distance travel is greater, the potential energy going to be greater or smaller? Going to be greater. It's going to be maybe positive 15 joule maybe. Okay, so when get closer, the potential energy get greater, maybe positive 18 joule and so on. But get away, the potential get weaker, maybe positive 8 joule and positive 7 joule. At infinite, if you're the potential at infinite, potential energy at infinite will be how much? 0 joule. No work has been done. To bring from infinity to infinity, the potential energy gain is 0 joule. Okay, that's the definition. Okay, so any question from this slide? Electric potential energy is work done to bring work done to bring a charge particle from infinity to that point. Unit is joule. It's joule. Okay. Derivation, no need to know, but you need to know how to use this formula. Sign of charge, please include. Okay, now comes electric potential. Electric potential. Electric potential is V. Is V, electric potential. Same like your gravitational potential. Your gravitational potential, what's the formula? Is negative Gm over R. Yesterday, I think I forgot to put the negative. It should be negative Gm over R. It's a gravitational potential. This mass is the center mass. Same thing go for electric potential. So what is electric potential? Electric potential of a point in electric field is defined as the work done in bringing a unit positive charge. This is to be added. Unit positive charge, 1 mark. Okay, unit positive charge to bring from infinity to that point. This is 1 mark. So you need positive charge to be included. Okay, so electric potential is work done per unit charge. Work done is actually potential energy. So potential energy, we know this is your potential energy. KQQ over R, just now we derived earlier. Divide by the test charge. The test charge, small q. This divided by the test charge, small q. Small q cancels. You get electric potential. This is electric potential. So you see, 4 pi epsilon, I put K. So it's become what? Become KQ over R. KQR. Same as gravitational potential. Just, of course, the constant is different. This is G, this is K. Here mass, this is charge Q, R. But no negative, no positive. Okay. So electric potential also, the sign of charge need to be, the sign of the charge must include. Must include. Okay. Don't forget to include the sign of charge. If the center charge is negative, then you must put the Q is negative. Okay, Q as negative. This Q is actually the center charge. Okay, a formula with 2 Qs. You have QQ. You have a center charge and the test charge. The formula only have 1 Q. Normally it would be the center charge. Okay, center charge. Okay, so KQR is the electric potential. What is the unit for electric potential? Is joule per coulomb, or of course the famous unit is volt. The one we use in electric is volt, joule per coulomb. But the definition is, last time we used to say define volt. What is volt in electric last time? A work done per unit charge, right? But the correct term is work done in bringing a unit positive charge from infinity to that point. That's called electric potential. Okay. So just let me show you something. Okay. Okay. So remember, if it's a positive charge, it's a positive charge at infinite. Okay, at infinite, let's say this is positive 5 coulomb. Okay. So at infinite, the potential will be how much? Potential at infinite will be
0.
0. When you get closer, the potential will get more positive, become more positive. If it's the center charge is a -5 coulomb at infinite, okay, and infinite, still the potential will be 0, but get closer, it become more negative. Okay, the potential get more negative. Okay, so potential get more negative. So yeah, this is the pattern. If this is here -5 joule per coulomb, the potential at this point A, and point B, it should be magnitude should be bigger, maybe 10 joule, but it's -10 joule per coulomb. The work done to bring a positive test charge, from infinity to this point is found to be -10 joule per coulomb. That means negative means you see this is center charge is negative, the test charge is positive. So actually, to make the negative and positive to get closer, do you need to do positive work? When to bring the negative and positive closer, you're going to move by themselves, right? So the work done by you is a negative work, negative work, because you never do any positive work. Like for example, you climb stairs, So when you climb stairs, you did a positive work or negative work? When you climb stairs, anyone? You did a positive work. You get sweated, you use your own energy to climb. But let's say you move down, let's say you jump from a certain height, you feel comfortable, you feel happy, you don't waste your energy, but work has been done because the earth pulls you down. So the work done by you is negative. Work done by you is negative. Same thing happens here. So negative center charge, you're bringing a positive test charge closer, the work done is negative. Okay, so work done is negative. Okay, so yeah, so this is the idea. So but for gravity, for case of gravity, this is the earth. I have to compare every time the gravity. For the gravity, earth. So earth gravitational potential, what's the difference between electric potential? Anyone? Earth gravitational potential at infinite will be what? 0. But when it gets closer, it's positive or negative?
Negative.
It's going to be negative. Good. Very good. It's going to be negative. Why is negative? We learned this reason. Why the work done by the earth is negative? Because this potential is caused by an attractive force. Caused by the attractive force. Any potential caused by an attractive force, the potential tend to be negative. So you can see the difference here. For electric potential, the electric potential could be positive and negative. It depends on the nature of the charge. But for gravity, the electric potential is always negative because only caused by an attractive force. Okay. If they ask the differences, this could be one of the difference. Electric potential for charge could be positive and negative, depend on the nature of the charge. For gravitational field, the electric potential is always negative because caused by an attractive force. Okay. Okay, good. So let me go back. Okay, go back to this slide. Okay, so KQ over R. Okay, electric potential is a scalar quantity. Okay, I just want to tell you, electric potential is what? It's a scalar quantity. It's a scalar quantity. Okay, it's a scalar quantity. Sorry. Something's wrong. Okay. Okay, so it's a scalar quantity. Remember, scalar. So scalar means electric potential don't have direction. You see this diagram. Let's say you have only positive. Let's say you choose a point P. You choose a point P. Let's say at the beginning you don't have these charges all. You don't have these charges all. I label it Q1, Q2, Q3, Q4, Q5. Let's say at the beginning only have Q1. Q1 close to P. Distance of R1. What is the potential caused by Q1 and P? So K Q1 over R1. That is the potential at P. Okay. Potential at P caused by Q1 positive or negative? Because Q1 is positively charged. So the potential caused by Q1 is positive at P. Okay. So let's say I put a number. Let's say I put a number. Q1 is, let's say, maybe positive 2 coulomb. Separated the point P. There is a point P. Let's see. The distance from point P is 1 meter. So what is the potential caused by potential? The electric potential V caused by the Q1 is K positive 2 over the R, which is 1. So it is actually 2K. I don't want to convert the K into value. You have to substitute the K. 2K joule per coulomb. That's the potential at P, positive. It's positive now. It's positive. Okay. So, so to bring a positive test charge from infinity to that point, there is a positive charge here. You have to do the potential you gain is positive. That means you have to do a positive work to come over here, because this positive charge is going to repel you. So you have trouble to come closer. Because this positive charge is going to repel you. So you have to do a positive work. Okay, let's say there is another positive charge Q2. Q2 was suddenly appeared into this system. Okay, Q1 is already there, produce KQ over R1. Q2 is come in. What happened to the potential at P? What happened to the work done to move a charge from infinity to that P? You need to do more work or less work now? Anyone? You have to do more work or less work now? Two positive charge nearby, So the repelling force get stronger. So for you to get closer from infinity to that point, you have to do more work or less work?
More work.
So you have to do more work. So the potential caused by now, just now the Q1 and Q2 alone. Now only Q1, Q2 is there. So the potential at P will be what? V1 plus V2. You see the formula, V1 plus V2. V1 is positive, V2 is positive because the nature of the charge is positive. Then if you have more charges, if you have negative, the V3 also added. But the V3 potential is going to be negative. It's going to be negative. And so on. So the total potential at point A will be all the potential added. So you get the final potential. Okay. So now tell me, is there chances you have a positive at P, the potential is positive 5 joule per coulomb, let's say. There is one positive charge, positive 5 coulomb is positive 5 joule per coulomb at P. Can you make the potential at P become 0? You bring what charge in nearer? You bring what charge nearer, the V could be 0. You bring a positive charge or a negative charge? You bring a negative charge nearer. Okay. Positive charge give you a positive potential at that P. If you bring a negative charge, the negative charge is going to create a negative potential at P. So the total potential at P will be these two potentials, the V1 and V2 add up. So it could be 0 if you have equal positive and negative charge. That means to bring from infinity to that point, the work you need to be done is 0 because one is repelling, one is attracting. You don't need to do any work. Work done is 0. One is pushing you, one is pulling you. So like you are net force 0, so work done is like 0. Okay, so you got the idea. So electric potential is a scalar quantity. It's a big relief because if they in exam they say few charges nearby, they're asking what is the electric potential at P. You just simply add all the potential. Okay, not like electric field. Electric field strength, if they ask, you have to draw a vector diagram. Force, if they ask, you have to draw a vector diagram, find the resultant. But electric potential, if they ask, just add them. They are scalar quantity. But one problem is electric potential, the charge sign need to be included. So the potential can be negative because depend to the nature of the center charge. Okay, any question from the explanation here? Anyone? Okay, I think you could understand better if I go to the next slide because a question. Okay, so yeah, guys, let's see. Recall back, your K is 9 times 10 to the power of 9. Okay, use this. Can you find what is the potential at P? What is the potential at P? At P, the V, the V at P, the V at P caused by these three charges. Two positive charge, one negative charge nearby. Okay, what is the potential at P? So calculate for me. Anyone? Anyone can tell me? Potential at P is actually what?
V1, V2 plus V3.
Yeah, V1 plus V2 plus V3. Tell me V1 going to be positive or negative?
Um,
V1 caused by the Q1. Positive or negative?
Positive.
V2 also. V2 also has V2. So yeah, V2 is negative.
V2 negative.
And V3 is positive.
Positive.
Okay, for V1, what is the distance you use for V1? V1, the formula is KQ over R. So V1 is use KQ1 and R1. R1 is how much? R1 is the distance from here to here. So this is your distance. This should be your R1. Okay, the diagonal distance. So you have to use the Pythagoras to find that distance for the R1. Okay, so for R2, R2 how much? I mean, for the Q2, R2 take how much? R2 is the coordinate. What is the coordinate? 0 point. Correct. This all in a coordinate system. Coordinate system. So the vertical height is actually y3 lah. Y3 0 1. So for V2, you put K Q2 over R2. The R2 should be 0 0.1 vertical height. Okay. For V3, the R should be what? R3 be the horizontal distance. The horizontal distance, how much? The x2, 0 0.2. Okay. Okay, so yeah, so this how should be calculated. So yes, so V1 plus V2 equals to V3. So take the distance. For the first one is 0 0.22, 0 0.1, and 0 0.2. So second potential is negative. The other two is positive. So finally it's found to be negative 4.8 kilovolt. So what is final conclusion? What is the final conclusion? To bring a positive test charge from infinity to point P, you have to do finally a negative work. That means although you have two positive charge and negative charges here, finally the net force is found to be an attractive force. Okay, I think Q2 is the winner compared to the two positive charges. I think maybe because you see the potential caused by negative is quite high. I think maybe because of the distance is short from the point P, very close by to negative compared to the positive. Yeah, that's the main reason. And charge is second largest, but I think the distance is quite short, gives us the greatest potential. That's why it's attractive force. Okay, so you got a negative 4.8. Okay, so tell me, if a charge move from here, from infinity, come close to P, it move close to P, okay, tell me, it will gain kinetic energy or potential energy? Negative 4.8 is the potential here. A charge move from infinity to this point, okay, it just from rest, it just move from here to here. It will gain kinetic will gain, or the potential will gain? Which one is gain? Because it's a negative potential. Negative potential. Negative potential means okay. In other words, what is potential energy and potential related? Potential energy and potential, the test charge times the potential difference actually, and the potential difference. This is the formula. This is electric potential energy, and this is your electric potential energy. KU. Last time we used EP, EP, electric potential energy. So now we use U. Okay. So the test charge, let's say you bring a positive test charge. So positive test charge is positive one coulomb. Okay. The potential difference is what? Potential difference. Potential difference is actually final potential minus the initial potential. Final potential minus the initial potential. Okay, tell me, what is the final potential value? Final potential, this is the final potential, final point you reach. Initial potential is at infinite. Final potential is found to be how much? Positive or negative? Negative 4.8 minus initial potential is what? Initial potential at infinity will be 0 So finally, what happened to the gain in potential? This gain in potential, the gain in potential will be how much? Positive or negative? It will be negative. Okay. So when a charge move from infinity, a positive test charge move from infinity to this point P, it's going to lose potential. The potential is negative. That means it lose potential and it gain kinetic. Gain kinetic. Okay, it gain kinetic. Okay. So in this case, the gain in kinetic should be equals to the loss in potential should be equals to the work done. Okay, work done by the field. Same means same in terms of magnitude. Their magnitude is the same. Their magnitude all as the same magnitude, same number. Okay. Gain means kinetic will be positive. Potential will be lost negative. Okay. Yeah. So the the magnitude going to be the same one. So remember, so this is how the potential energy and kinetic energy is related. Okay. Okay. So yeah. So you see this diagram. A positive charge move from RA to RB. Okay, move away RA to RB. The electric potential VAB between the 2 points in electric field is work done in taking the one column of positive charge from A to B. Work done is QVAB. Yeah. So what is the work done to bring from here to here? What is the work done? How much is the work done? Work done is Q changes in potential as stated here. As stated here. VAB is the potential difference between VAB is actually final potential, which is V at B minus V at A. Moving from A to B. So final potential is VB minus VA. It's your work done to move from A to B. Okay. So please tell me, the center charge is a positive charge. Let's say the one column is a positive one column. Okay. The test charge also positive one column. To move from A to B, tell me VB greater or VA greater? Anyone? The test charge, the center charge is positive Q. The test charge also positive one column. To move from A to B, okay, the potential at B greater or potential at A greater? In terms of okay, what I can say, in terms of positiveness, which is more positive? Anyone? So VB greater or VA greater? Both are positive charge. The test charge moving from A to B. VB greater or VA greater? Anyone? Should be VB should be greater than VA. VB should be greater than VA. Sorry, I made a mistake. Which should be greater? The other way around, right? VA should be greater than VB. VA should be greater than VB because of what? The test charge, the electric potential dependence what? The work done to bring from infinity to that point what? A is more further away. A is more further away, so work done is greater. So VAB will be greater. VVB be smaller, less work done because shorter distance. So VAB definitely greater, VA definitely greater than VB. So tell me, work done to bring from A to B, the work done, going to be positive or negative? Because VA is greater than VB. VA is greater than VB. Okay, VB is greater than VB is greater than VA. So therefore, the work done going to be positive or negative? It's moving A to B. So A is greater than B, so it's going to be negative. Okay, the work done going to be negative. Okay, it's going to be negative because VA is greater now. VA magnitude wise greater than VB. So finally, you got a negative answer. Let's say you got negative 5 joule. Okay, so that means negative 5 joule means, tell me, this 5 joule is gain in kinetic or gain in potential? Gain in kinetic or gain in potential? Positive charge, and this also positive charge. The positive charge is moving away. Positive, positive separated further. So this positive charge, the test charge, will gain kinetic or gain potential and go away. Anyone? Positive and positive. Yeah? Gain kinetic or gain potential?
I think it's kinetic.
Very good. So it's gain kinetic. So remember the work done is negative 5 joule. So you must remember, because positive, positive get further, you should gain kinetic. The gain kinetic energy is 5 joule. It lost what? It lost potential. The potential, the U, sorry, I put the symbol U. U is 5 joule. Loss is 5 joule. Or potential, potential lose 5 joule. Okay. Positive, positive get further. So taking charge from point lower potential to higher potential results in the charge gaining the potential energy. The reverse movement of position of higher potential to lower potential analogs to a free falling under gravity, where the object loses potential energy and gain kinetic energy. In this case, it gain kinetic, lost potential. Okay, lost potential. Okay. So this is a very important term. Before I go to the next slide, okay, let me go back to the whiteboard to strengthen this idea. Okay, again, let me clear this. Okay, you see here, okay, you have a positive 5 column, you have a positive 2 column here, is a test charge. Okay, this you can assume as a capital Q, this as a small q. Okay, so this charge move from A to B, this is your B. So this charge move from A to B. Okay, tell me VA, VB, which is greater? VA or VB greater? Anyone? It's the center charge is positive 5 column. VA greater or VB greater? So V is what? V is work done to bring a unit positive charge from infinity to that point. And the formula for V is what? KQ over R. Which R? R from here, R from here, right? And which Q? The Q supposed to use the Q of the center charge. Okay. So now tell me, VA greater or VB greater? Which one is greater? Should be VB, right? VB greater. VB should be greater because center charge is positive 5 column. Positive 5 column. So work done to bring from infinity to this point, longer distance, VB is greater. VB should be greater. Because greater distance. Or you can use this formula. Okay. Because R is shorter and Q is positive. So VB should be greater potential. Okay. So now if you move from A to B, moving from A to B, so work done is positive or negative? Anyone? So what is work done? Q, final potential minus the initial potential. That is the work done. Q is the Q of the test charge now. So Q, final potential is what? Final point, final place is B. It's B. So it should be VB minus VA. VB minus VA. Because VB is greater than VA, this is going to give you a positive answer. And the test charge also is a positive test charge, going to be positive. Therefore, the work done going to be positive. Okay, work done going to be positive. Oh, easy to visualize. Positive and positive get closer. And positive, positive get closer. The work done is positive. Difficult for us to move closer. You have to do work. You have to work, make the positive get closer. So you do a positive work. So work done is positive. So gain in potential. So let's say positive work done. Let's say it's positive 10 joule. Let's say I give a value positive 10 joule. So this is gain in potential or gain in kinetic. This 10 joule is a gain in what? This will be gain in potential 10 joule. Okay. Lost in kinetic, we say 10 joule. Lost in kinetic is 10 joule. Okay. Yeah. Tell me, if the center charge is negative 5 column, you bring a positive 2 column from A to B, here, okay, A to B. Tell me the work done, going to be positive or negative? Anyone? Should be negative. Should be negative. Negative, getting closer to positive. You don't need to do work. What you're going to move together by themselves. It's an act of the own field. So you're going to attract it. So work done is going to be negative. Okay. If work done is negative, it means it's gain in kinetic or gain in potential. When you come from A to B. Anyone? It should be gain in kinetic. Gain in kinetic. Kinetic energy will rise. Potential energy, we say, is lost. Is lost. Okay. So negative work done means gain in kinetic, lost in potential. Positive work done means gain in potential, lost in kinetic. Important. Remember. Okay. The question asking for what is potential energy, what is kinetic energy, you need to calculate the work done. You need to calculate the work done. Q changes in V. You need to calculate so that we can find the potential energy. Okay. So potential gain means kinetic definitely lost. Okay. Okay, good. So let me ask you another one question. Okay. There is a positive 5 column here. A negative 2 column was at A. Okay. About a distance of 2 meter away. Okay. The negative 2 column has been fired. With the with the initial kinetic energy of, let's say I put let's say that's 10 millijoule. Okay, so the negative 2 column was fired away from positive 5 column, which possess a 10 millijoule of kinetic energy. Okay, 10 millijoule of kinetic energy. Okay, so the question is, you're going to stop somewhere B. You're going to stop somewhere B, right? Because this is positive charge and this is a negative charge moving away, fired away, force them to move away. But eventually this positive are going to attract it, pull it back. So you're going to slow down, of course, you're going to stop somewhere. Okay, the question is, what is the distance you're going to stop? Okay, so how do you going to find this distance? I put this as D. So how do you find this distance? So how are you going to relate them? Okay, so how do you find the working? The lost in EK, it must be equals to what?
Gain in
Gain in potential. Yes, we can go for gain in potential. We can go for lost in EK's gain in potential. So gain in potential, how do you find gain in potential? Gain in potential, what is the formula of potential energy? Potential energy, we can use test charge times the final potential, which is VB minus the initial potential, VA. That is your gain in potential. Okay. Yeah, should be equals to the, of course, this is going to be a positive answer. It's going to be a positive answer. Okay. So here, how do you put the lost in kinetic? Lost in kinetic. So this is going to be the BBA. The lost in kinetic will be how much? 10 millijoule. The 10 millijoule. We put 10 millijoule. Okay, 10 millijoule equals to Q. Post Q is the test charge will be what? The test charge is actually negative 2 column. VB is what? VB we don't know, but VB we can put as what? K. Which Q? The positive 5 over which R? R will be what? 2 plus D. 2 plus D. It's moving from where to where? Yeah. Okay. 2 plus D because the total distance. Okay. Total distance from the center to the B. Minus VA should be what? VA is K negative 5 the test charge over what? Over 2. Cable 2, we can find the D. We can calculate the D. Okay. So this is how you need to do the working. Lost in kinetic equals to gain in potential. You make them positive, yeah, you can get the answer. Okay, so this is how you have to do the questions.
So
Yeah.
is -5 or +5 for
Oh, sorry.
the
Negative.
calculation?
Or should be positive 5.
Both, right?
Yeah, both positive 5. Yeah. So the charge is positive 5.
All right.
Okay. Okay. So let's see the questions there. Okay. So one question about what we have done so far. Look at the question. Look at the working. Hope it makes sense for you. Okay, so they're asking for what? 2 positive point charge, 12 microcoulomb, 8 microcoulomb, separated for 10 centimeter apart. Okay. So at the beginning, both of them 10 centimeter apart, and they are bringing them 4 centimeter closer. The 10 centimeter separation, they brought to 6 centimeter of separation. Okay, what is the work done in both charges? Okay, so they're asking for what? Find the work done. Okay, find the work done. Find the work done to bring them 10 centimeter separation to 6 centimeter. So one is positive 2 microcoulomb. Another one is positive 8 microcoulomb. They separated by 12 centimeter at the beginning, 10 centimeter at the beginning. This was moved closer. We come here, which is only now is 6 centimeter. So they're asking what is the work done. Nicholas, without calculating, tell me, the work done going to be positive or negative? Work done is Q, the final potential minus the initial potential. Or you can check the easy way. You check the nature of the, what do you call the type of charge. Positive 12, positive 8. Get closer. Work done positive or negative? It's going to be
Positive.
It's going to be positive. Very difficult for us to make two like charges closer. So you do a positive work, you get sweat. Okay, when you make them closer. So you do positive work. So positive work, yes. So that's working here. Okay. So yeah, the Q equals to V final minus V initial, or you can use what? You can use the potential energy. Okay, the final potential energy is what? Separation. You can use the final potential energy minus the initial potential energy also can. Final potential energy formula is what? Is QV final. QV final is actually final potential energy. What? QV initial will be the initial potential energy. So you can use KQ over R also. KQ over R. Q times potential, also you get KQQ over R. KQQ over R. Substitute all the values. Make sure the sign of the charge is included. So you get answer. So of course, the work done is positive. The potential energy gain will be positive also. Potential energy is gain. Kinetic energy is lost. Kinetic energy should lost by 8.6 joule. 8.6 joule should be also lost in EK. Lost in EK. Okay. So they are getting the this is the initial potential energy, and this is the final potential energy. So the difference in the potential energy is your gain in potential energy. So it should be 5.8, not 8.6. So 5.8 is your work done, and the positive work done, 5.8 joules. Okay, the loss in EK also must be 5.8 joules. So finding final potential minus initial potential energy differences is your gain in potential energy. Okay. So any questions from here?
No.
Okay, next, you see now the next part. What is the work done if both charges are negative? Now instead of positive 2 microcoulomb, positive 8 microcoulomb, now this is negative 12 microcoulomb. This is negative 8 microcoulomb. When you get closer, you do positive work or negative work? Yeah?
Negative work.
Positive.
Negative 12 coulomb, negative 8 coulomb. You get closer. You get sweat, or like it's going to get closer by itself?
You need to sweat.
You sweat. Okay. So you have to do a positive work, right? You have to do positive work because it's going to repel. Like charges going to repel what? So if you want to make them closer, you have to do a positive work. The work going to be positive. Okay. If you not realize, you just do Q, final potential minus initial potential. The final potential finally going to be bigger than the initial potential. You will get a positive answer when you put the numbers. So negative 12 and negative 8, negative 12 and negative 8 get closer. You do a positive positive work. That means gain potential or lose potential. Potential energy. Gain or lost? It will be a gain. You'll gain potential. You'll gain potential. The kinetic energy will be a lost. Okay. So that's the answer here. If both charges are negative, the gain the gain in potential is still 5.8 joule, still 5.8 joule, still positive. The work done is positive. The charges are opposite. Okay, so this is going to be positive. So no changes. If both are negative charges. Okay. So look at the third one. What if one is positive and another one is negative? Okay, so one is positive 2 microcoulomb, another one is negative 8 microcoulomb. So you get closer, work done definitely going to be negative. So the gain in potential energy will be the gain in potential. You gain potential or lose potential when you get closer. The gain in potential energy will be negative. Or in other words, we can say you lost potential. Okay, so you gain kinetic. Gain kinetic will be positive. So remember, if work is negative means gaining potential also negative. Okay, I think the work is same sign as gaining potential. If work done is positive means the gain in potential is positive. Okay, so potential and work is like always same sign. Work is positive means gain in potential is positive. You gain potential. When you gain potential, you normally slow down. Kinetic is lost. Okay, so that's why positive charge, the gain in potential is negative 5.8 joule. Opposite charges lost potential when brought closer together. Okay. Okay, so that's about potential. Okay, before we go to these graphs, yeah. So these are the graph going to change for potential. Potential energy, this potential energy joule, is in terms of joule. Joule versus R. Okay, R is the separation of the two charges. Okay, when the two charges are, let's say, like charges, when they get closer, when they get the R get closer, the potential rises. Potential energy, sorry, the potential energy rises. Potential energy rises because positive when get closer, you sweat, you do work, you did a positive work. So when the particle is quite close, the particle already gained potential energy, gain a very high potential energy. That's a very high potential energy. When you let it go, you're going to move fast further because you have great potential energy. So the potential energy will be very high, positive. It's going to be positive. and get get close to zero when very far further away. So what is the potential energy formula? K Q Q over R. That's the potential for energy formula. So potential energy versus R is going to make a inverse graph. It's going to be an inverse relation, U and R. Okay, so you see the next graph here. The next graph is for positive and negative. The positive and negative, one is positive, another one is negative. Potential definitely going to give a negative value. Okay, so that's why the graph is drawn at the bottom. It's negative. Okay, negative potential. Okay, so positive and negative and get closer. When positive and negative get closer, it loses potential. Okay, so when you let it go, this negative won't go away. It just stick together. They don't have potential. The potential is negative, farly negative, very negative. Okay, tell me, our gravity, Earth as the capital mass and you as a small mass, the gravitational potential energy, going to be which graph? Exactly same as the first one or the two? Anyone? The Earth and you, the gravitational potential energy. When you get closer, the potential energy you possess is going to follow the first graph or the negative graph. Positive or negative, the potential energy you possess. Anyone? Your case, Earth and you, is exactly situation like charges or unlike charges? Unlike charges, like same as your unlike charges, because you are attracted to the Earth. So when you get closer, your potential become more negative. So for Earth and you, it follows the same as the second graph, same as the second graph. Okay. So yeah, what is the potential energy for the gravity? Let's recall back. What is the potential energy formula for gravity? Is negative G mm over R. So same as your gravity electric potential, K Q Q over R, but without sign. Negative gravitational potential energy is negative. Okay, any questions from here? You can. Okay, before we go to this slide, let's we strengthen the idea. Okay, we need to do some questions to get this idea from top. Okay, we go to some questions. Okay. So this is the word file again. So we learn about electric potential is KQR. KQR. The relation we come back. Okay. This all skip. We go to this questions line. Okay. Question 2. So recall back what you learned today. Get me the answer for the question 2. Today you learn V equals to KQ over R. V is work done per unit test charge. Okay. Then you learn electric potential energy. Electric potential energy is Q changes in V. Changes in V. It's your V. The Q final V minus initial V. So normally you get K Q Q over R. The final minus initial. K Q Q over R is your potential energy. Okay, use the first one. I think you need to use the second one. You can think about the third one also. Yeah. Question 2. hope everyone get the answer in the bracket. A charge of 3 coulomb is moved from infinity to point X in an electric field. The work done in the process is 15 joule. What is the electric potential at X? So everyone agrees 5 volt. So there's the electric field at the center charge. We don't know what is the center charge. We don't know the center charge. Okay, we don't know the center charge. A test charge we know. A test charge was how much? A test charge of 3 coulomb was moved from infinity to one particular point. The point, okay, moved to a point. We label the point. Okay, is the point. And you see, to move from here to here, the work done is positive 15 joule. They're asking what is the potential here. So which formula to use? 1, 2, 3. I think you have to use the fourth one. This one. So what is potential? Definition is work done to bring a unit positive test charge from infinity to that point. The work done is 15 joule, and test charge brought is 3 coulomb, positive 3 coulomb. So it have to be 5 volt. Okay, you have to be 5 volt. The work done to bring from infinity to that point is only 5 volt. Okay, so answer should be 2. Okay, any problem with the working? So work done per unit charge to be used. Okay, so if you don't have problem 2, think about 3 now. Okay, I give you 1 minute for you to do 3. Give a try 3. Okay, use this formula 3. Try to get the answer inside the bracket. So let me rub this. Okay, do you get the part A answer? What formula to be used for the part A?
The first one.
First one.
The first one. Yes, good. First one. So water, a drop of water which is spherical in shape carries a charge of 3 times 10 power 8. So spherical of water droplet carries a charge of 3 times 10 power of negative 11 coulomb. Okay, we assume it's a positive charge because no sign. So what is the electric potential at the surface? Of course, KQ over R. The Q is the center charge, it's positive 3. And the R is the center from the center to the point where you want to find the potential. So the radius of the sphere. Okay, so A is easy. So the potential, the radius is found to be 5.39 times 10 power negative 4 meter. Okay, the second one is tricky. Those who getting the answer 794, final answer. Okay, good. I'll give you another 1 minute. Come on. B. So the two drops with same radius combine to form a larger spherical drop. Or the drop like this, two drop combine form a larger drop, larger one. Okay, larger one. So for this drop, they're asking what is the potential at the surface. So again, we have to use which formula? The first one. You have to use the first one, right? Potential at the surface. But now two drop merge. What is the charge going to be? Charge going to be two drop at. So the charge going to be times 2, right? 3 times 10 to the power negative 11, just times 2. The two drop merge. So the two charges merge. The charge is just times 2. But the problem is the radius. How much is the radius going to be? Can you simply make the radius double than this? Can the radius become like 5.39 times 10 to the power negative 4 times 2? You can't, right? You can't. You have to find the volume. It's based on volume, you have to calculate the new radius. Okay, the two volume of this, the V1 plus V2. V1 plus V2 is the two volume of the first small drop is equals to the volume of the larger one. From here, you need to find the radius of the larger one. So what is the volume formula for a sphere? You have to use that. What is the volume formula for a sphere? 4/3 pi r cube, right? So use that 4/3 pi r cube, 4/3 pi r cube. The larger one also 4/3 pi r cube. Find the r of the larger one. Then only you substitute in here. You should get 794. Okay, so those who have idea in your mind, the volume need to be added equals to the volume of the larger one. Okay, you are in a correct track lah. Then find the radius. Okay, so 4/3 pi r is how much? The small one. Yeah, the one you got now. 5.39 10 to the power of how much? -4. -4 cube. We just times 2 times 2 because both volumes same one. Is equivalent to the new volume of the big sphere, large sphere, pi r cube. Let's find the r first. Then the voltage at the surface will be K. Q is what? Q is 3 times 10 to the power of -11 over the this R, whatever R you get here, the R you place down here. So you should get 794 if your unit conversion all correct. Okay, yes. So I believe you get the answer. No problem. So you got the idea. Okay, can we move to another one? Move to another one. Okay. So we go to number 4. Okay, just learn the technique. Okay, number 4, I scroll down. Okay, number 4. Tell me the answer for this. Hope you get the answer in the bracket. You need to get these two answers. In a helium nucleus, two protons are separated by a piece of glass. Find the electrostatic force between the two protons. I think that's easy, right? What formula you use for the first force? Coulomb's law. Two proton separated by what distance? 1.5 times 10 power negative 15. And what is the force? So use Coulomb's law. K Q1, K Q, PQ small q over R squared. One of them we take capital Q, another one we take small q. So yeah, R squared. Nature of the sign of charge no need to include, so you get the force. K is 9 times 10 to the power of 9. K is 9 times 10 to the power of 9. So I believe all of you got 102 Newton. Okay, the charge of proton is what? It's the elementary charge. It's 1.6 times 10 power of negative 19. Charge of a proton. Same as charge of electron, right? So use this charge. K is 9 times 10 power of 9. R is 1.5 times 10 power negative 15 meter. So I think you get 102 Newton. Okay. Okay, the next one, maybe you need to think a little. What is the work done against this force to bring the two proton from infinity to the given separation? So what is work done? How much is the work done? Work done. Work done to bring the proton from what? One proton we imagine is at the center. One proton we assume that is already there. Another proton we bring from infinity to this point. The point of the separation from infinity to that point. You're asking what is the work done to bring these two separation? So work done is the same as what? Q. What? Final potential minus the initial potential, right? That's your work done, right? Then you get the answer. Now, who going to be the test charge? One of them going to be the test charge, one of them going to be the center charge. It's okay, it's because both of them same. Maybe this you take it the capital charge, the center charge, another one is the test charge now, right? Okay, you imagine one is Q, capital charge, another one is the test charge, moving closer. But in your mind, work is Q, final potential minus initial potential. Okay. So do you get this answer? 1.53 times 10 to the power negative 15, negative 13, sorry. What is your final potential? Final potential 0 or initial potential 0? Anyone? Which potential is 0? Final 0 or initial 0? Because it's moving from infinity to that point. So here is the final potential. Initial potential is at infinity. So which potential 0? Initial potential must be 0, right? So the work done is Q times final potential only. Final potential only. So Q times potential is what? KQ over R. So you substitute all of them, you get this answer. The sign of charge need to be included. Both are positive, so you get a positive answer. Okay, so any problem? Can get the idea, eh? So work done is positive or negative for this case? I think you get a positive answer. Work done is found to be positive. That means you gain potential or gain kinetic. The body gain potential or kinetic. The body gain potential. Potential is gain. Potential gain is positive. It might lose kinetic. If it was fired from infinity to get closer to the P, it will lose kinetic. Okay, the lost kinetic is same as the gain in terms of magnitude. Okay. Okay, guys. Any questions about 4? I believe you get the idea how to do. No problem, eh? Okay. So I assume all of you understand how to do that because I wanted to maximize the number of questions we do. We go to the next question. Number 5. Okay, look at number 5. Give me the answer. So what is the charge required to rise the electric potential of a conducting sphere to this much? If the radius is 1 meter. Like a Venn diagram, Venn diagram machine. You have a sphere. How much charge need to be kept here? What is the charge required here so that the surface has a potential of this much? I think this is straightforward, right? So, Venn diagram, due to friction, the rubber going, due to friction, you can induce charges on the Venn diagram surface. Normally, it will be positively charged. Okay, so more charges, more rubbing, more friction when the what do you call the belt is run for a long period of time, more duration, more friction, more graded charge will accumulate on the sphere. When the charge builds up, the potential at the surface is going to increase. So potential is what? K Q over R must come to your mind. This is the formula. Electric potential is K Q over R because it's like a point charge sphere. So what is the charge required for build up a potential of 1 times 10 power of 6 volt? The radius of the sphere is found to be 1 meter. 1 meter, quite big. So you can find the charge. The charge should be 1.11 times 10 power negative 4 coulomb. Okay, so the formula must come to your mind to do question 5 is B equals to KQ over R. So the charge needed at the surface to build that voltage, this is the formula. Okay. Okay, any problem with 5? You must think about KQ over R. Okay, I don't know, many of you have seen Venn diagram machine. If you prolong charging the sphere, the amount of charge accumulated on the sphere increases, the voltage at the surface tend to increase. There'll be a point where the air particle will start to ionize. Okay, the air particle will start to ionize. Okay, in exam they do ask why the air particle ionized. What makes the air particle ionized? 3 marks question they asked. Why the air particle can ionize when the voltage builds up on the surface of the sphere? So of course, the different interest, right? The electron was attracted to the sphere because unlike charges, but the nucleus inside the molecule in the gas particle is nucleus which is positively charged, repelled from the sphere. Okay, so there'll be a point when the voltage is quite strong, the electron will strip off from the atom, the gas molecule, so results to ionization. When ionization happens, what do you get? Get kind of like a spark happens. Spark appears. Spark appears. And the voltage is quite huge. Okay. The voltage is quite huge until you can pull out the electron from the atom. Spark will happen. Ionization happen. Okay. So air become conducting now. Okay. So any questions for today's lesson? So these are the 4 things you learned today. Okay. Please give a try the complete working for the question 2, 3, 4, and 5. I explained to you. Get working. Okay. The 6 is the another part I need to explain to you. Explain to you electric potential. Okay. I can do that next class. Okay, class. Because next week you have biology from Wednesday to Friday, is it? Wednesday to Friday, Okay. Can we have the class on Tuesday? Tuesday 10:30.
Yeah.
Would be okay. I sent to the WhatsApp. If anyone got any concerns, you can't attend, you just text me. Maybe we can change it. So my plan is next week is Tuesday 10:30 to 12. And Friday, can I put it maybe around 1 o'clock after your bio class? Should be okay, right? So my suggestion is next week is
Right.
Tuesday.
Sir,
Yeah.
this Friday or next Friday?
Next Friday, not this Friday, next week Friday.
Okay.
Next week Friday we have on Tuesday and Friday lah. Next week Friday.
Friday, I think we got chemistry until can.
Yeah.
Until
Okay, right.
Chemistry until 1. Okay.
You have biology also on Friday, right?
Yeah.
Oh, you have 3 lessons then. All of them 1.5 hours, is it?
No. We're different class.
Different class.
Okay, so we can have it on then. So Friday we have it at 1 o'clock, 1 to 2:30, and Tuesday is at 10:30 to 12.
Yeah.
Okay, class. We almost done with this topic. You can do the past years. Okay, on Monday, I think about half an hour I finish this topic. Then we do some questions. Then we see how. If can, we can go to the next topic. Okay. At the background, you must do lots of questions. A2 is quite short period of time. You must do 3 times more hard working than your AS. Okay.
Mm.
No questions, we can stop here.
Okay, thanks, teacher.
Thank you. Bye.
Thank you, teacher.
Okay.